Welcome back. Good day, everyone. In today's video, I'll be embarking on a journey on equilibrium constant. Equilibrium constant. This is another topic you likely see in your exams. The question states, write out the equilibrium constant for the following. We have A, we have 2, number 3, number 4, and then the last one, which is the number 5. The equilibrium constant K, it is denoted by this symbol. Please, this must be in capital letter. This symbol K is gotten from the use of the law of mass action. The law of mass action, I believe you remember. So that is where this capital letter K came from. Don't forget that. And this K can be in two dimensions. It's either in K subscript C or K subscript P. If it is KC like this, please, the K is a capital letter. Take note of that. If it is in KC, this C is for concentration, and this concentration is talking about remember, mole per dm cube. And if it is for P, it's talking about partial pressure. Partial pressure. And this one here deals with gases. So the constant for equilibrium, the constant for equilibrium reaction, it can be in form of Kc or Kp. For Kc, it's talking about concentration in mole per dm cube, while for Kp, talking about gases, and it means the P there stands for partial pressure. So please take note of these reactions. That's my first, the second, third, fourth, and this is fifth reaction. But before we start this, I wanted to bring your mind back to chemistry. In chemistry, if you have a reaction like this, plus B to give us C, differs from A plus B forward and backward reaction to give us C. And this one differs from A plus B. You have something like this, okay, yeah, to give us C. Now, let me explain this first structure. This is a resonance structure of C, is a resonance structure of A and B. For example, benzene is a very good example of this. Talking about having a benzene structure of such, and another benzene structure of this nature. Yeah, yes. So this is a resonance structure. These two structures, they are the same. Just talking about movement of electron, of pi electron rather. So in this reaction, it's talking about a straightforward reaction, and it is irreversible. It is an irreversible reaction. Why this is a reversible reaction? And this is what we are talking about in this very topic, equilibrium constant. And take note, the AB, all what we have here, they are the reactant, they are the reactive species, they are the reactant, while all these ones here, we call them the what? The product. So please take note. And if you want to write the equilibrium constant for any reaction, there is something you need to take note of, which is the coordination sphere. This is what we call the coordination sphere. I repeat, the reactant, product, Kc, concentration in mole per dm cube, Kp, partial pressure, and something about gases. And this is what we call the coordination sphere. So let's come back to this. If I want to write the equilibrium constant for the reaction I have there, AA plus BB is equals to CC plus DD. I'll write, let's say, solution K is equals to product all over reactant. Please, this is just the basis. So from here, you can get whatever you are looking for. So the first thing, you write your coordination sphere, or your equilibrium concentration. You can call it equilibrium concentration or coordination sphere. So I'm going to go to my product first before coming to the reactant. Please, this A here is the number of mole, B here is the number of mole. Assuming the A is here, A can be a subscript. But since A is before the element, is a number of mole, number of mole, number of mole, number of mole. So I'm going to write C. Let me write only the element, D, all over the product. Then the coordination sphere again, A, B. Now, if you look at this closely, this is not the correct answer. We have number of mole that is missing here. We have number of mole that is missing in all the compound. So if it's a number of mole, I will take it to the power. But assuming it was a subscript, it will remain here. For example, assuming I have C here, I'm going to have C here. It's going to be inside. But since there is no C here, since we have just the number of mole, it will be raised to the power of the number of mole, raised to the power, raised to the power, and here will be raised to the power of what? Of B. So this is the first one, the answer to this first one. Then for the number 2, I will say my K is equals to, remember, it is product all over the reactant. So if this is product all over the reactant, my product is ammonia. So I write NH3. This is the compound. This is the subscript. It's going to be inside. Then is there any number of mole there? Yes, 2. So it will be raised to power 2 all over. Then we have hydrogen here. I will place my hydrogen H. Yes, there's a subscript there. Then there's a molecule here. It will be 3. Then I will now come to my nitrogen N2. Is there any number of mole? Yes. What is there? 1, but 1 is already invisible. So that is my answer. Please take note. The subscript can be inside, but the number of mole must be taken to be the power. Then let me try this very well for you. Then I believe you can do this, and you can also do this. I believe that this one is more simpler. Let me just do number 4, because I believe you will be kind of confused. Minus. So if you have H plus all over CH3 COOH, I believe this is correct. No, this is not correct. This is wrong. Remember, it is reactant all over the product. So what you are going to do is this. You are going to take these ones here, you bring it down, and you take this one, you take it up. You write the reactant phase before the product. And these charges, all these charges here, they are going to be inside the equilibrium concentration. They are going to be inside. Assuming we have a number of moles here, here is 1, here is 1, they are invisible. Assuming we have 2, 3, 4, 5, we are going to take them as their power, but this is wrong. Jamb might also decide to stress you by giving you a particular value for ammonia, a particular value for hydrogen, a particular value for nitrogen. Now let's assume ammonia was given to us to be 2, hydrogen is given to us as 1, hydrogen is 1, the value of hydrogen and nitrogen is half. So what I'm going to do is this. I'll write 2 divided by 1 raised to power 3 times nitrogen is half times nitrogen. So it will be equals to 2 here, 2, yes, raised to power 2. Please take note of the power so that you won't make any mistake. So raised to the power of 2 will give us 4. 1 raised to the power of 3 will give us 1. It means 1 times 1 times 1. Everything equals to 1. So times half. My half will be here. 1 times half will give us half. So I will have 4 divided by 1 all over 2, which is also the same thing as 4 times 2 all over 1. If I'm changing this in mathematics, remember, you invert. So that's just what I did. So my answer will be equals to, my answer is equals to what? Is 8. So please take note of all this. And this 8 has no unit. There is no unit for the equilibrium concentration, equilibrium constant rather. So please, I want you to try this. Try this. I've done this, I've done this, I've done this as well. But I believe now in this reaction, I'm going to write this all over this, which is the product all over the reactant, which is also wrong. This is not an equilibrium reaction. This is a straightforward reaction. And in straightforward reaction, you can write the equilibrium constant for it. All these ones here, the reason why I'm able to draft all these whole things out is because of this sign I'm having here. It's showing that you can go to the product and you can as well come back to the reactant. So if you have any questions based on this, feel free to drop it in my comment section. Thanks for watching.